The universe keeps surprising us and challenging our everyday intuitions. After demolishing 35 misconceptions about our solar system, it's time to explore failed stars, space dangers, and the challenges of space exploration. Why Jupiter was never destined to shine, why atmospheric re-entry is way more complex than friction, and why Mars is far more hostile than Hollywood led us to believe. Stay with us, because these will probably be the last 7 of the series. Jupiter was about to become a star. People often say that Jupiter is a failed star, or that it almost became a star but didn't quite make it. This romantic notion suggests that the gas giant nearly succeeded in igniting like the Sun. In reality, Jupiter was never even close to becoming a star. To trigger hydrogen fusion reactions in its core, an object needs to reach a critical mass of about 80 times Jupiter's mass, roughly 0.08 solar masses. Jupiter has a mass of only 318 times that of Earth, but the Sun is 1,048 times more massive than Jupiter. So we're not talking about almost. Jupiter was missing 99% of the way there. Even to become a brown dwarf, substellar objects that can fuse deuterium but not hydrogen, you'd need at least 13 Jupiter masses. Jupiter falls far short of even that threshold. Its composition, mainly hydrogen and helium, is similar to stellar composition, but that doesn't mean it was on the verge of igniting. The stellar formation process is radically different from planetary formation. Stars are born from the gravitational collapse of enormous molecular clouds that can contain enough mass for hundreds or thousands of stars. Planets, on the other hand, form from the leftover protoplanetary disk around an already formed star. Jupiter followed the planetary path. It was born as a rocky core that then accumulated gas from the circumsolar disk, a process that stopped when available material ran out and the solar wind from the young sun swept away the residual gas. Jupiter does emit more energy than it receives from the Sun, about 1.6 times more. But this doesn't come from nuclear fusion. It's simply residual heat from its formation continuing to radiate into space, combined with energy released by ongoing gravitational contraction. This phenomena is common to all young giant planets. The solar system is as old as the universe. Many people think the solar system formed shortly after the Big Bang, or at least in the universe's early stages, as if stars and planets were original cosmic features. Well, want the truth? The solar system is surprisingly young compared to the universe. The universe is about 13.8 billion years old, while the solar system is only 4.6 billion years old. That means the universe already existed for 9.2 billion years before our sun ignited. About 2/3 of cosmic history had already passed. Right after the Big Bang, the universe contained only hydrogen, helium, and traces of lithium. The heavier elements, carbon, oxygen, silicon, iron, and all the others that make up rocky planets and our own bodies, simply didn't exist. These elements formed in the cores of stars through stellar nucleosynthesis and were then dispersed into space through stellar winds and supernova explosions. The solar system is a third-generation stellar product. The first stars, population 3, were enormous, made only of hydrogen and helium and burned rapidly before exploding as supernovae. Their ashes enriched interstellar clouds, allowing the formation of second-generation stars, population 2, with greater metallicity. The Sun belongs to population 1, stars relatively rich in metals born from material already processed by previous generations of stars. The molecular cloud that gave birth to the solar system contained remnants from previous supernovae. We have direct proof in meteorites, where we find isotopic anomalies that reveal their origin in stellar explosions. Some short-lived radioactive isotopes found in primitive meteorites indicate that a supernova exploded nearby just a few million years before the solar system formed, perhaps triggering the very collapse of the cloud that gave rise to the Sun. This means that Earth, with its oceans and life, is a relatively recent phenomenon in cosmic history. Extraterrestrial civilizations might exist on planets born millions of years before ours. Sunspots are dark and cold. Looking at images of the sun, sunspots appear as dark zones, leading many to think they're cold or dead regions of the solar surface. Well, no. Sunspots are dark only by contrast, but they're anything but cold. They have temperatures around 3,500 to 4,000 degrees Celsius, or 6,300 to 7,200 degrees Fahrenheit, while the surrounding photosphere reaches about 5,500 degrees Celsius, or 9,900 degrees Fahrenheit. In absolute terms, sunspots are scorching hot, hotter than most red dwarf stars. If we could isolate an average-sized sunspot, typically a single spot can measure over 50,000 kilometers or 31,000 miles across, and project it in the sky, we'd see it shine as bright as the full moon. Sunspots form where intense magnetic fields, up to 4,000 Gauss, thousands of times stronger than Earth's magnetic field, burst through the photosphere, which, to be clear, is the sun's apparent surface. These magnetic fields inhibit the convective motions that normally transport heat from the interior to the surface. Convection is the main mechanism by which heat is transported from deeper layers. Without it, that region becomes relatively cooler, but still blazing hot in absolute terms. The number and size of sunspots vary with the roughly 11-year solar cycle. During solar maxima, the sun can display dozens of spots, some as large as the entire Earth or bigger. These regions are associated with intense magnetic activity and can generate solar flares and coronal mass ejections, events that hurl high-energy charged particles into space. Paradoxically, then, the dark sunspots are indicators of zones of intense activity and magnetic energy, not inert or cold regions. Re-entering spacecraft heat up due to air friction. The classic image is of a space capsule rubbing against the atmosphere during re-entry, generating heat through friction, like when you rub your hands together to warm them up. In reality, heating during atmospheric re-entry is mainly due to adiabatic compression of the air, not friction. When a capsule re-enters from orbit at speeds of 7 to 8 kilometers per second or 4.3 to 5 miles per second, over 15,000 miles per hour, it violently compresses the air in front of it. This sudden dramatic compression leads to an enormous increase in gas temperature. The phenomena follows the same principle that makes a bicycle pump work. When you rapidly compress air, it heats up. In the case of atmospheric re-entry, the compression is so extreme that the air in front of the capsule reaches temperatures of 1,650 degrees Celsius or 3,000 degrees Fahrenheit or higher, hot enough to ionize the gas, creating an incandescent plasma. True friction, called viscous heating, does contribute to heating but is secondary. The dominant physics is that of the shockwave that forms in front of the vehicle. This shockwave abruptly slows the air from the vehicle's supersonic speed almost to a standstill, converting enormous kinetic energy into heat. The heat shields of space capsules are designed to manage this heat through ablation. Materials like phenolic resin or PICA, phenolic impregnated carbon ablator, heat up, melt, and vaporize in a controlled manner, carrying away the heat and creating a gas layer that insulates the rest of the capsule. The front part of the shield is shaped, generally with a blunt form, to create a detached shockwave that keeps the hottest plasma away from the surface. During re-entry, radio communications are interrupted for several minutes, the famous communications blackout, because the ionized plasma surrounding the capsule shields radio waves. This is clear evidence that we're dealing with high-energy plasma physics phenomena, not simple mechanical friction. Our moon is the largest natural satellite. Earth's moon appears enormous in our sky and has considerable dimensions, diameter of 3,474 kilometers or 2,159 miles, leading many to believe it's the largest satellite in the solar system. Sorry to disappoint, but the moon is only the 5th largest satellite in the solar system. The largest is Ganymede, which orbits Jupiter, with a diameter of 5,268 kilometers or 3,273 miles, bigger than even Mercury. Following are Saturn's Titan, 5,150 kilometers or 3,200 miles, Jupiter's Callisto, 4,821 kilometers or 2,995 miles, and Jupiter's Io, 3,643 kilometers or 2,264 miles. Only after these four do we find our moon. However, there's one aspect in which the moon is truly exceptional: its relative size compared to its parent planet. The moon has a diameter equal to about 27% of Earth's diameter, an extremely high ratio. By comparison, Ganymede has a diameter of barely 3.7 compared to Jupiter, and Titan is about 4.4% compared to Saturn. This unusual size ratio has led some astronomers to consider the Earth-Moon system almost as a double planet rather than as a planet with a satellite. Only Pluto and Charon have an even more extreme size ratio. Charon is about 12% of Pluto's mass, but Pluto is classified as a dwarf planet. The moon's origin is linked precisely to this anomalous size. The most widely accepted theory is the giant impact hypothesis. About 4.5 billion years ago, a Mars-sized protoplanet called Theia struck the primordial Earth. The impact was so violent that it vaporized part of the mantles of both bodies, projecting material into orbit. This material reaggregated, forming the moon. This catastrophic origin explains several peculiarities. The moon's low density, it lacks the large iron core we'd expect, the chemical similarity with Earth's mantle, and the high angular momentum of the Earth-Moon system. Analyses of lunar rocks brought back by the Apollo missions confirm this close kinship with Earth. A nuclear-armed missile could destroy an asteroid about to impact. Hollywood has conditioned us to think that, faced with a threatening asteroid, the solution is to send a nuclear bomb to blow it up, reducing it to harmless fragments. Movies like Armageddon have crystallized this image in the collective imagination. We haven't tried it yet, but apparently destroying an asteroid with a nuclear explosion is much more problematic than it seems. First of all, there's no atmosphere in space to transmit a shockwave. Much of the energy of a nuclear explosion on Earth is carried by the atmospheric shockwave. In space, the weapon would release mainly radiation, X-rays, gamma rays, and a particle stream, but without a medium to transmit pressure. Even assuming you detonate the device on the surface or inside the asteroid, the most likely result wouldn't be complete pulverization, but fragmentation into smaller pieces. The problem is that these fragments would continue to travel approximately along the same original trajectory. Instead of a single devastating impact, we'd have a rain of fragments, some of which might still be large enough to cause catastrophic damage. Asteroids aren't monolithic blocks, but are often rubble piles held together by gravity, aggregates of rocks and dust. An explosion might simply rearrange the fragments, which would reaggregate once the shockwave passed. The use of a nuclear device therefore remains a last resort option, but it would be employed to deflect, not destroy. The explosion would be detonated near, not on the asteroid, vaporizing material from one side that would act like a rocket engine, pushing the asteroid off course. Time is the critical factor. With decades of advance warning, small corrections are needed. With months of advance warning, no current technology could guarantee safety. That's why near-Earth asteroid detection programs are so important. On Mars, we could survive for a short time even without a spacesuit. There's a widespread belief that in an emergency, a human could survive on the surface of Mars for a few seconds or minutes by holding their breath, like they would underwater before returning to a pressurized environment. But is that really so? The answer is no. Exposure to the Martian vacuum would be immediately lethal, and not for the reasons people usually think. The atmospheric pressure on Mars is about 0.6% of Earth's, roughly 6,000 pascals, equivalent to the pressure at 35 kilometers or 22 miles altitude on Earth. This pressure is below the boiling point of water at body temperature. What does that mean? The water in your tissues would start to boil, a process called ebullition. The saliva on your tongue would boil, fluids in your eyes would begin to vaporize, moist tissues in your nose, throat, and lungs would do the same. Your body would swell dramatically, up to twice its normal size, as gases dissolved in bodily fluids expand. You wouldn't explode like you often see in movies, but the tissue damage would be catastrophic and irreversible within 10 to 15 seconds. Holding your breath would make things worse. The air in your lungs would expand violently, causing pulmonary barotrauma, ruptured lungs. The correct procedure in case of explosive decompression is precisely to exhale immediately. The average temperature on Mars is minus 63 degrees Celsius or minus 81 degrees Fahrenheit, with excursions ranging from plus 20 degrees Celsius or 68 degrees Fahrenheit at the equator in summer to minus 125 degrees Celsius or minus 193 degrees Fahrenheit at the poles in winter. Freezing of exposed tissues would be rapid. Solar UV radiation unfiltered by the thin atmosphere would cause immediate burns to skin and eyes. The absence of a significant magnetic field exposes the surface to cosmic radiation and solar particles. Prolonged exposure would cause cellular damage and drastically increase cancer risk. But even brief exposure would contribute to the damage. Experiments conducted in vacuum chambers on Earth have shown that a human exposed to Martian pressures loses consciousness within 15 seconds due to lack of oxygen to the brain, and without rapid pressure restoration, brain death occurs within 90 seconds. The documented survival record for an explosive decompression accident is a few minutes with permanent damage. Martian spacesuits, therefore, aren't simple, optional protective equipment. They are complex life support systems that provide pressurization, temperature control, breathable oxygen, carbon dioxide removal, radiation protection, and communications. Without them, Mars is as instantly lethal as the vacuum of deep space. Okay guys, here we are at the end of the journey through the most common planetary misconceptions. The last one, unless you want to suggest other false beliefs for us to debunk. Is there anything that particularly impressed you in this overview of correct interpretations of the laws of the cosmos? Is there anything you found unconvincing and would like clarification on? Let us know in the comments, and don't miss the other episodes of the series.